Okay, welcome back. Today we're going to continue our discussion of clustering, and today we're going to tackle the question of what do you do if you don't know the number of clusters that you need to find. And the technical tool that we'll be using to address this is something called Bayesian nonparametrics. And so the Gaussian mixture model that we talked about last time is a probabilistic model, unlike k-means, and it has several latent variables. So for each cluster, you have the mean of the cluster. For each data point, you have what cluster gets assigned to. And then you can also have the variances like we talked about last time. Last time we were doing something called EM. I didn't talk about that, but this is called expectation maximization. And here we're basically having a probabilistic model with some parameters, and when we don't know the answer to one of these latent variables, we basically just take the expectation of that and then pretend like that was the truth. And so when we figured out the means, we're basically taking the expectation based on a current set of assignments. And so today we're going to talk about new models and new methods for figuring out the latent variables in a probabilistic model. But what's going to be different is that we don't know the number of clusters. And so this is why this is called Bayesian nonparametrics. And so nonparametrics is just a fancy statistical way of saying that you don't know one of your parameters and you can add more parameters as you need them. And we'll add more clusters as we need them to explain our data. And Bayesian is just a way of saying that we have a Bayesian probabilistic model over our clusterings. Terminology okay?
Yes.
Okay, all right. So now let's get into the Dirichlet process, which is a general framework that we'll use to talk about our clustering. And so the Dirichlet process and the Dirichlet distribution are both distributions over distributions. So that's a little hard to wrap your head around, but we'll walk through that. And so we often talk about the Dirichlet process as being a two-parameter distribution. The two parameters are alpha and g. Alpha is a concentration parameter, and g is your base distribution. And so the way to think about a Dirichlet process is as a black box that you can stick a distribution into, and then another distribution comes out of it. And g is the distribution that you're putting in, and the thing that you're getting out of it is the output of the Dirichlet process. And alpha controls how similar g is to g prime. And then you can draw observations from the thing that you got out of your Dirichlet process. And so you get some g prime out, and then you can draw x from that g prime. Okay, so the very formal way that you can define how this creates new versions of your distribution is that you can draw a bunch of v variables from a beta distribution parameterized by 1 comma alpha. And so these will look like numbers between 0 and 1, depending on what alpha is. And so this could be 0.1, 0.4, 0.8, and so on. And you have an infinitely many set of v's that you then create into what are called stick breaking weights. And the metaphor for doing this is that you have some long stick, and each v tells you how much of the stick you're going to break off. And so you start breaking your stick up, and so if your first break comes in here, then this is how much weight is going to be assigned to C1. And now you have the rest of the stick to play with. And then you look at your next V2. This tells you how much of the remaining stick to break off, in which case you might have that. And you just keep doing this out to infinity. And so you end up with smaller and smaller little chunks. Okay, so here are sort of your weights. And now we're going to approximate our original distribution G by drawing from that. And so these are called atoms. And so we're just going to draw these atoms from our G, and then we're going to merge them into a complete distribution where you basically have a machine that takes, for each atom, a weight for that atom and the atom itself, and then it creates a new distribution, and it asks, something comes in, you say, is this equal to this atom? If it is, then it has probability CK for all of the times that it matches.
Wait, see, what was that delta right there?
This is a Dirac delta. And so this is just asking, is the input equal to phi k?
It's almost the same as the indicator.
Exactly,
Okay.
yeah. But this is the notation that's typically used in talking about the Dirichlet process, so very much like that.
Okay.
But this is just the notation that gets used in this case, and other folks like to use the indicator. Okay. So here are some properties of a Dirichlet process. So the expectation of x drawn from G, drawn from a Dirichlet process, is equal to, or G prime, I guess I should say, is equal to the expectation from the original distribution. So this makes sense. You're using the Dirichlet process to change some distribution G, but the expected value will be the same. Another thing is that it's impossible to completely represent on a computer because computers don't have infinite memory, and this is an infinite set. But you have to truncate at some point, but that's usually okay. You can also nest Dirichlet processes. So you can have H from a dp of G, and you can have, then you can have J from a dp of H. And so this is a lot of fun, and if you took the NLP course and you remember back off, this is how we accomplished that in the NLP course.
Do other statistical properties remain the same? The expectation value is the same. Does the variance change?
The variance does change, and in fact it depends on alpha.
Okay.
Okay, so here's an example of draws from a Dirichlet, here are examples of a Dirichlet process where the base distribution is a normal Gaussian. If alpha is small, then you'll have very few points with high probability. If alpha is larger, then you get more points with higher probability, and it begins to look a little bit more like the Gaussian, but not quite. It's not as concentrated in the center as you might expect. You can also change the underlying base distribution. If you make that normal much tighter, then the resulting Dirichlet process will also look tighter about the mean. So here are some examples of how you can use the Dirichlet process to basically create discrete copies of continuous distributions. But this works for any underlying distribution, but we'll talk about Gaussians today. All right, so why have we been talking about this? You can also use this as a way of doing clustering. So you can basically say, my centers will come from a Dirichlet process whose base distribution is a Gaussian. And so this is why we're talking about this in the first place. We draw some points. These have some weights. And then we'll create new little Gaussians around each of the points that we draw. And each of these draws will be a cluster. So this is cluster 1, cluster 2, and cluster 3. And then our data can come from any of them. And so if it comes from cluster 1, it will land in this area with high probability, cluster 2, this area, cluster 3, this area. So this is how you can get to clustering from a Dirichlet process. And the neat thing about this is that a Dirichlet process has an unbounded number of atoms. And so you basically figure out which Dirichlet process most likely generated your data. So you're inferring the weights of each of your clusters and the means. And in figuring out the number of atoms with high probability, you're also figuring out the number of clusters. All right, so now let's move to how you can do inference in Dirichlet processes. So there's a metaphor called the Chinese restaurant process to explain how Dirichlet processes work. So the way that the statistical Chinese restaurant process works is you have a bunch of tables, and you have people seated at these tables. And so you have some new person who walks into the restaurant, and they sit down at a table with probability proportional to the number of people sitting at the table. And so in this case, 2/7 probability here, 3/7 probability here, 2/7 probability here. And then once they sit down at a table, each table is associated with a dish, and that corresponds to the mean of this cluster, say, and then you draw an observation with probability, say, normal with mean of the dish of that table. Okay, but at this point you might say this is just maximum likelihood. Why are we talking about Chinese restaurants? The way that this came about is that the people who invented Dirichlet processes lived in Berkeley, and they had this experience of going to Chinese restaurants in Berkeley, and one restaurant in particular, you went in, and you could always get a table. They were able to find you a new table somewhere. And so the Chinese restaurant process does that. So in addition to sitting at an existing table, you can sit at a new table with probability proportional to alpha, where alpha is the parameter of the Dirichlet process that we were talking about. And then you also need to draw a new mean for that new table. Okay, so now the question is, we have this model, we have the Chinese restaurant process, how do we figure out, given a bunch of data, what cluster assignment each one goes to, and then the parameters associated with each cluster? All right, so the way this works is you take a random guess initially. This provides a mean for each cluster. So then we're going to let the number of clusters grow or shrink as needed. And the cluster assignments will correspond to tables, and we'll use the Chinese restaurant process to incrementally change all of our assignments, and then we'll just update that observation by observation. And this is called Gibbs sampling. And so what we're trying to figure out is we're trying to find out the assignment of each data point to a cluster. And we'll assume that each data point depends on a clustering of its neighbors, so all of the other observations, and then whatever parameters our probability distribution has. So the concentration parameter of the Dirichlet process, the base distribution, the other data, what have you. And we'll just keep doing this forever, or until we get tired of it. And there's some fancy math you can do to prove that this will converge to the true posterior distribution. We won't go through that. There's an optional reading if you want to know more about that. And then one little bit of notation I want to talk about is that we'll call z minus I all of the z's except for this guy. And so that will make it easier just to say the probability of zi given z minus I. Okay, any questions thus far? Okay. All right, so what we want to do is we want to sample cluster assignments for every point based on the cluster assignments of other points, the data itself, and the means associated with the tables and the concentration parameter. So the first thing that we'll do is we'll drop out irrelevant terms. If we're just asking what's the probability that this guy is associated with cluster K, it only depends on cluster K. It doesn't depend on all of the clusters. Next, what we'll do is we'll apply the chain rule. And so the dish at the table, the mean of this cluster, is related to X, but what table we're sitting at only depends on how many other people are seated at the table, not what they actually are. So we'll apply the chain rule. And now, what we'll do is we'll try to integrate out the means of the tables. And so this is some hairy calculus that I won't go into. So let's ignore these integrals for now, and by magic I will give you the answer in a second. It also depends on what the underlying form of these guys are, so we'll assume that they're normal distributions. But this part here is relatively straightforward. This is just the number of people seated at an existing table divided by the total number of people sitting at all the tables plus your concentration parameter. And then for a new table, it's just proportional to alpha over n dot plus alpha. So this is just the Chinese restaurant process seating probabilities. Okay, so there are some scary integrals, but they turn out just to be normal distributions. And for existing tables, the mean of that distribution is basically just something almost like the average of those points, but with an extra term in the denominator. And then for a new table, it's just the probability of coming from a simple Gaussian with mean 0 if we assume certain things about the base distribution. This in particular, that it has mean 0 and 0 variance. And unit variance, sorry. Yep.
That extra term in the denominator is just how the math works out. It's not any like Laplace smoothing.
No, exactly. Okay. Well, actually, it's a little bit like that, and so Gaussians also have a prior, and so this is assuming the way it works out is it's like you're assuming that you have an additional observation with 0 mean. And so it is a lot like Laplace smoothing. Okay. And so with Laplace smoothing, you're assuming that you see every observation one more time. And in the Gaussian case, the way this works out, it's like you're seeing another observation with the mean of your prior. Okay. In this case, it's 0. So it's like we're adding in plus 0 here. And then you have an extra count from adding in that plus 0.
Yeah.
Okay, so the algorithm for this is we're assigning our clusters randomly initially, or however you want, really. So just start with some initial assignment. And then for each iteration, you're going to unassign observation in. And so you're basically going to pretend that you're seeing this observation for the very first time and assign it to a cluster. And the reason that we're unassigning it is because the math for Gibbs sampling says that you want to compute the probability of Zi conditioned on everything but Zi. And so that is equivalent to just basically pretending that this point doesn't exist, and then computing the conditional probabilities of this guy conditioned on all the others.
So
Yep.
Unlike k-means, it doesn't matter. You don't have to have a good initial assignment.
In theory, yes. In practice, you still want to have a non-stupid initialization.
Because I imagine it would be faster.
Yeah, exactly. It will converge faster. Yeah, but the theory says that if you run your sampler long enough, you'll converge to the posterior. Okay. But in practice, people are impatient. You still want to initialize well. All right, so here's a toy example. So we'll initialize every point being in its own cluster, which is not the greatest initialization, but this is a toy example. So first what we do is we unassign, say, this point, and say, all right, we need to figure out what cluster this point lives in. And so the way that you do that is you're going to compute a term for each of the existing clusters, in which case there's a cluster for every data point. And so this term will be how many people are seated in that cluster. In this case, it's basically 1 over the number of clusters, which is 1, 2, 3, 4, 5, 6, plus alpha. And then you're going to add in a term that's basically something like what we had for the mixture of Gaussians, which is the distance from x to the mean squared. And then if you might have a variance term in there as well, we'll forget about that for the moment. And so you compute this for each of your 6 clusters, and so it will vary based on the mean. And then you're also going to compute a term creating a new cluster. So alpha over 6 plus alpha times x minus your prior mean. So you can create a new dish for a table, and you need to rate the compatibility of this guy to that new dish. All right, so you get these 7 terms, and then you sample from that distribution, and you'll get a new cluster assignment. So let's say that it went with this teal cluster here, and so now this teal cluster has 2 points. All of the other clusters have 1 point. Okay, so now we sample another point, and so here for this cluster, you'll have something like 2 over 6 plus alpha, and for this point, you'll have 1 over 6 plus alpha plus the compatibility, plus or multiplied by the compatibility, and then you also have a term for a new cluster, alpha over 6 plus alpha times the compatibility. And again, you cluster, and it's pretty close to this cluster here, and this cluster is more popular, so it's almost certainly going to, again, join the teal cluster. So things get a little bit more interesting once you get to this point here. And so here you unassign it, and what might happen in this case?
Could the weight of that table coerce that point to join it?
Yeah, so that's one possibility. And so if for instance, this is now fairly popular, and this might not be that far away, it may join that. But so that's one option, perfectly reasonable. Another, but what if this distance is actually fairly far? What might happen in that case? And by symmetry, this distance is also fairly far. What might happen in that case?
It might just end up being reassigned again to its own individual class.
Yeah, and in that case, so once we uncolored it from purple, that cluster went away because it became empty. And so if it ends up in its own cluster, that is a new cluster. And so in that case, it's creating a new table in this Chinese restaurant with probability alpha over 6 plus alpha times the compatibility of creating a new cluster. So we've created a new cluster, and this is what the Dirichlet process can do. So if it doesn't like any of its options for the other clusters, it's not like k-means, and you just have to go whichever one is closest, you go to it, you can create your own cluster and say, I'm hanging out by myself, hopefully other people will join me. And then you continue on, you can resample the other points, and maybe you get a cluster here. If you've been paying attention, I hadn't sampled this point yet. You should sample all of your points, nor did I sample that one. So you should sample all of your points, and you can repeat this as much as you want and eventually you will converge to the true posterior. All right, any questions?
The order in which you sample the points won't matter because it's going to converge anyway.
Yeah, and in practice, a lot of people just, you have some ordering in your data naturally, and you just go through everything and repeat. Ideally, you should randomize your order, but a lot of people are too lazy to do that.
Okay.
All right. Comparing what we were doing before and Gibbs sampling is often faster to implement. There are fewer things to, fewer messy pieces of code you have to write. It's easier to tell when EM is finished because basically things stop changing and you know you're done. Another nice upside of Gibbs sampling is that it can be applied to a wider class of models. But the flip side is that EM can often be parallelized fairly easily. So if you're at Google or something like that, oftentimes EM can be stupidly parallelized across thousands of machines. Whereas Gibbs sampling, because you basically have this connection from one point to every other point, and that changes everything, it's a little bit harder to parallelize. All right, so in class, we'll walk through an example of clustering with the Dirichlet process mixture model. And next week, we'll be talking about how to do clustering when you have more than one cluster per observation.